yesterday we were finding all these volumes, and to do it, what we did is found the area of a cross section and integrate it from the starting point to the stopping point. Okay, but just like when we did areas, sometimes the equations are ugly and you maybe can't solve for y, so we have to keep the y's. So we might have to integrate in terms of y at times. The process is the same, but just like with areas, if you are going to integrate with respect to y, then your upper and lower limit have to be y values. Your equation has to have y in it, and you have to have a dy at the end. So you have to be consistent. Either everything is an x or everything is a y. You can't have a mixture of the two. So let's look at this one. I want the volume of the solid obtained by rotating the region bounded by y equals x cubed. So we know x cubed, that's the chair, right? So it looks like this. Y equals 8. If it's y equals, what kind of line is that? So we've got this horizontal line at 8. And x equals 0, which is a vertical line. So far it doesn't look too bad. What region are we really looking at then? We want the region bounded by all of those, so the part in between all of them. So really, we're just looking at this right here, correct? But here's what changed. I'm rotating that about the y-axis. So if I take that and spin it around the y-axis, okay, we get something like this. Now, this is definitely y equals x cubed, that's in terms of x. X equals 0 is in terms of x, but here's what's weird, what's different. If we were to integrate this on the x-axis, do you have the same smallest and biggest x the entire way through? No, it varies. But do we have one highest and lowest y value? Yes, because we spun around the y-axis, so we have our low, we have our high. So this one would be better to do in terms of y. So if I'm going to do that, we need to first figure out when x is 0, can we agree y is 0 there as well? 0 cubed is 0, so we're going to go from 0 to 8. And this will be a dy. Okay, a cross section. So if you take a slice of this, now to get a slice, which way would you cut it, up and down, or would you cut it horizontally? You cut it horizontally, which is another indicator that we need to use that y value. Okay, so if I look at that slice, what shape is it? Circle. Area of a circle is pi r squared. So we need to know the radius. The radius goes from the center all the way out to this black line. What's the equation of that? X cubed. But these are in terms of y. So I have to solve this for x. So how would we get the x by itself? So the cube root of y is equal to x. So we're going to roll from 0 to 8. Pi. That would be y. Cube root is like a 1/3. Squared would be a 2/3. So if you add 1 to the power, 2/3 plus 1 is 5/3. So we would put 3/5 in front. Okay. So 8 to the 5/3. That's the cube root of 8, which is 2. To the 5th is 32. Minus 0, so we get 32 times 3 pi over 5, or 96 pi over 5. Is that one okay? So what we have discovered, because that's happened on every problem, if you take any kind of curve, we're assuming all above the x-axis or the y-axis, and if you spin it, we get circular cross sections, right? Even if this was kind of an irregular curve to start with, so this one started with this to begin with, but even as you spin that, you're still getting circular cross sections. So we are able to just integrate those. This is what's called the disk method. That's what we've been doing every time. I kept telling you pi r squared. Well, in the disk method, the radius is just your function. So that's what we've been doing. Let's look at this one. What the volume of the solid forms when the region enclosed by the curves y equals x. What's y equals x look like? That's just a line. Y equals 0, slope 1. And y equals x squared. What's x squared? Okay, so if I just want the region enclosed by those, what region am I looking at? Just this. Okay, so when I'm rotating just that part, so that's the only portion we need, and I'm rotating that about the x-axis. So for my rotations, I always kind of think of like flipping it first. How is this different than the others? Yeah, it's a little triangular, and the very center is hollow, isn't it? So what we've created is more of like a funnel type thing. So it's hollow in the middle. We really just need that outer rim, the volume of that. Okay, so think about when we did areas.
Please dismiss track athletes. Please dismiss track athletes on the list at this time.
How did we do areas when we had something like this? Not add, but we subtracted to get the part in between. So that's what we're going to kind of do here. So we know if we set this up, we need to find the intersection. Would we agree, since we spun around the x-axis, it would be easiest to do this in terms of x? So you need to know when the equations, x equals x squared, so you get x equals 0 and 1. Alright, so I'm going to integrate from 0 to 1. What kind of shape would a cross section be? Still circular. So that's pi radius squared, and we're doing it all in terms of x, so dx. So the radius, if you look at this circular cross section, so you have an outside and you have an inside, okay? And we want, so to get this shaded part, we would have to do the outside minus the inside. Okay? But we need to be a little more careful. When we go to set this up, we don't want to square the whole thing. We want to think of it as, all right, we have an outside function, so we'll do that circle and then subtract off the inside circle. So we are going to do each one of these squared, because we're going to do outside circle minus inside circle. All right, which one is on the outside, the furthest away? Y equals x. So we'll have x squared, and then the inside one was y equals x squared, so that would be x squared. So antiderivative. Antiderivative of x squared. What do you want to do?
This side.
Do you not have a copy?
No, I wasn't here yesterday.
Somebody might have already taken my extra one. So I just did my integral, didn't I? That's what I get for talking while I'm integrating. That goes at the end. So you get pi. You put in a 1, you get 1/3 minus 1/5. Put in a 0, those are both 0. So we get 2 pi over 50. Okay, so how was this problem different than the previous ones? It was hollow. We had two curves we were rotating at the same time and looking at the part contained between them. So in that kind of scenario, if you have two functions that are rotating at the same time, it will be hollow in the middle, and so that is the washer method. So it's basically taking the area of the outside minus the area of the inside, and then integrating. Let's do one or two more. We'll probably stop for today. Alright, so let's find the volume of the solid obtained by rotating the region in example 6a about the line y equals 2. So, I have the same initial setup. We had the y equals x and the x squared, right? Those were the two we started with. But now we're rotating that around y equals 2. Where is, so we found, let me try to move this down. Okay. When we did this, we found our intersection points were at 0 and 1. Okay, if you plugged in a 1, that y is also 1, right? 0, 0, and 1, 1. So y equals 2 is up here. And I'm wanting to rotate around that line. Still didn't leave myself enough room. Made it too big. Okay. So if I go to spin around this line, think of it as like reflecting first. So this point would come up to here. This one was one away from the lines. This one. Maybe I spin. So again, this is shaded here. So the outside is there, but it's hollow on the inside. All right. Would we do this one in terms of x or y? Well, it's not real obvious, is it? But we spun it around a horizontal line, right? The x-axis is a horizontal line. When we spin around the x-axis, what variable do we usually integrate with respect to? X. So let's do it in terms of x. So we'll go from where to where? 0 to 1 still. And still a dx at the end. Okay. Now we have to think about a cross section. So the cross section is still circular. But the radius is not measured from the axis anymore. It's measured from 2, isn't it? So to get the radius of the outside, what do you have to do? When you start at 2, if I want to measure the distance from here, down to here, this is x squared, this is 2, so to get that radius you have to do 2 minus x squared. So, our pi, the outside radius is 2 minus x squared, and we have to square it because pi r squared, minus the inside function. So if you start at 2, at this time you would only go down to that line, which is x, so 2 minus x squared. I'm going to pull out my pi, and then I'm going to FOIL each of these. We distribute the negative and combine like terms. 4's drop. 4. 5x. Antiderivative of x to the 4th. 1/5 x to the 5th. Minus antiderivative of 5x squared. Plus antiderivative of 4x. X squared from 0 to 1. Get 8 pi over 15. So we aren't limited to only spinning about the x-axis. We can spin about other lines. Okay, we will try more of those tomorrow. I'm going to give you guys some more to do on your own, but all of these are spinning around an axis, so they'll be more straightforward. So you are ready to do 4, 5, 7, and 9. Add it to last.